Hi friends, in solid state we have already studied what is meant by crystal lattice and how unit cell is related to crystal lattice. Today we are discussing about the characteristics parameters of a unit cell. Each unit cell is characterized by 6 parameters. They are 3, edge length and 3 angles. In this picture you can see that we have 3 axes along the x axis, y axis and z axis. This is 3 axis. Along the x axis, if it is origin, along the x axis it make an intercept at A. Similarly, along the y axis we have intercept at this point and along z axis this point. So we have 3 edge length. One is this one, that is represented by A. Next one is along the y axis distance is B and along the z axis distance is C. And 3 angles, alpha, beta and gamma. Between y and z alpha, between x and z beta, between x and y gamma. These are the 6 parameters which we need to represent a unit cell. In last class we have already discussed about the classifications of unit cell. They were primitive unit cell, that means simple cubic system, then face-centered, body-centered and end-centered. They have a short representation like P for primitive, F for face-centered, then for body-centered we have I as the symbol and end-centered we have C. Depending on the variation in these 6 parameters, what are the 6 parameters? ABC, 3 edge length, alpha, beta, gamma, 3 angles. Depending upon the variation in the 6 parameters, we will get different shapes for unit cell. So far, we have identified 7 crystal systems: cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal and rhombohedral. Variation in shape of the unit cell can be seen clearly here. The relation between edge length and angle for these 7 crystal systems can be tabulated here. System are 7 in number. They are cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal and rhombohedral. Relation between the edge lengths are: edge lengths can be given as, for cubic system all the 3 edge lengths are equal, A equal to B equal to C. For the last system also A equal to B equal to C. For the second system, A equal to B but not equal to C. That is true for second last system also, A equal to B not equal to C. Now we have 3 systems: orthorhombic, monoclinic and triclinic. They have all unequal. A not equal to B not equal to C, A not equal to B not equal to C, and A not equal to B not equal to C. Okay, this is true for orthorhombic, monoclinic and triclinic. Coming to the angles, for cubic system it is alpha equal to beta equal to gamma equal to 90. That is true for next two systems also. For monoclinic system, alpha equal to gamma equal to 90 degree, but beta not equal to 90 degree. Triclinic is nothing is equal. Alpha not equal to beta not equal to gamma not equal to 90 degree. And for hexagonal, alpha and beta equal to 90, but gamma is 120. 120. For rhombohedral, alpha, beta and gamma are equal, but not equal to 90 degree. For rhombohedral system, it is inclined to one side, therefore angle is greater than 90. Now in BL does not means bone length, it is bravais lattice. What is bravais lattice? There are 14 different ways bravais lattice. LATTICE. If you have been given with a particular lattice point or constituent particle, you can have 14 different ways, 14 different ways to arrange that constituent particle or lattice point. That possible arrangements are called bravais lattice. For cubic system, it is P, F, I. P, F, I. P means primitive, I means body centered, F means face centered. For tetragonal system, P and I. Orthorhombic, P, F, I, C. C means edge centered, end centered. For monoclinic system, primitive and end centered. Thereafter we have primitive only. How to understand it? For first system, cubic system, primitive, that is simple, face centered and body centered. For orthorhombic, they have all possibilities. All possibilities means these four possibilities: primitive, face centered, end centered and body centered. Here we have primitive and body, here primitive and end centered. So 3, 4, 2, 2. That's over. Thereafter, all of them have primitive only. An example, for cubic system we have the example sodium chloride, potassium chloride, etc. Along with it we can include alum, diamond, lead, gold, etc. For tetragonal system we have tin stone, that is SnO2 and tin. Few more examples can be seen in your textbook that you can check. For orthorhombic system we have gypsum, and KNO3, barium sulfate, sulfur, etc. For monoclinic system we have sulfur and also borax, similarly gypsum, etc. Gypsum can have two forms, monoclinic and orthorhombic. Sulfur can also have two forms, orthorhombic and monoclinic. Depending on the temperature and other conditions, they can exist either in orthorhombic or in monoclinic form. Triclinic, that is an unsymmetric system where example is K2Cr2O7, that is potassium dichromate, copper sulfate pentahydrate, etc. For hexagonal, most common example is graphite. Graphite has hexagonal layer arrangement that you have studied in previous semester. Along with it, we have cinnabar, HGS, mercuric sulfide, zinc oxide, cadmium sulfide, etc. For rhombohedral system, we have NaNO3, iodine monochloride, ICl, etc. These are the 7 crystal system and the corresponding bravais lattice. So totally we have 14 bravais lattice, but we have only 4 fundamental bravais lattices: primitive, simple, that means simple cubic, then face centered, body centered, and end centered. These 4 possibilities are varyingly present in different systems: 3, 2, 4, 2, 1, 1, 1. Totally 3 plus 2, 5 plus 4, 9 plus 2, 11, and then totally we have 14. So we are winding up the session on bravais lattice and 7 crystal systems. And in the first session of this class, we have discussed about the number of parameters required for describing a unit cell. Thank you.